let's go ahead and do another example problem. In this example problem, we're going to be going ahead and analyzing a heat exchanger. So this problem statement is saying that I have R134A entering at one side of the heat exchanger at a pressure of 1 megapascal and a temperature of 90 degrees Celsius, and it exits the other side of the heat exchanger at 1 megapascal and 30 degrees Celsius. On the other side of the heat exchanger, I have air flowing in at a volume flow rate of 600 cubic meters per minute at a pressure of 100 kilopascals and a temperature of 27 C, and is exiting at the other side of the heat exchanger at 95 kilopascals and 60 C. So if you remember, a heat exchanger is an engineering device that allows two fluids to exchange heat between each other without mixing. So typically, in most cases, not all cases, but most cases, we can assume that my heat exchanger is adiabatic, and that and then if we put the system around the whole heat exchanger, right? If we assume it to be adiabatic, meaning no heat loss to the environment from the heat exchanger itself. So some assumptions that can follow for this heat exchanger is one, this heat exchanger is operating at steady flow. You also notice that on one side of the heat exchanger we have air, and on the other side of the heat exchanger we have refrigerant, meaning one fluid is air, one fluid is refrigerant. So we can assume that the air is an ideal gas. And I'm going to go ahead and assume an ideal gas with constant specific heats. And I'm going to assume that the change in potential and the change in kinetic energy is 0. Now, for this heat exchanger, the problem statement is asking us to solve for the mass flow rate of the refrigerant. Right, so we have the volume flow rate of the air, but it's asking for the mass flow rate of the refrigerant. So for a heat exchanger, the way to analyze it actually depends on how you take your system boundary. So for this heat exchanger, we can take our first law analysis with the system around, or the boundary around the whole heat exchanger. That's one way. In that case, if you notice, if we assume that the heat exchanger is adiabatic, where no heat crosses the boundary, remember, all the heat is exchanged inside the boundary. So I'm only interested when I do a first law analysis at the energy crossing the boundary. So if my boundary is around the whole heat exchanger, the only energy crossing the boundary is in the form of mass. So that's one way I can take my first law analysis. Another way to do this would be to actually draw my boundary around one of the fluids. So if I did that, for example, if I were to go ahead and draw my boundary just around the refrigerant, you notice that the refrigerant is cooling. So the refrigerant is actually giving up heat to the air. So if I do my first law analysis around the refrigerant, I have energy in by mass, energy out by heat, and energy out by mass. And I could also take my first law boundary around the air as well. So I'm going to go ahead. I'm going to do this problem three ways. I'm actually going to solve the problem by doing a control volume, or my boundary, around the whole heat exchanger. For the second, I'm going to go ahead and as a second analysis, I'm going to go ahead and take my boundary, my control volume, around the air. Around the refrigerant. And I'm also going to do it around the air. So let's go ahead and start with doing the control volume, or the boundary, around the whole system. So first way we're going to do this is a first law with the boundary around the whole heat exchanger. So let's go ahead and start. So we have energy in minus energy out equals the change in energy of the system. This is a steady flow problem. So the change in energy of the system is 0. So that means that all energy in by heat, mass, and work equals all energy out by heat, mass, and work. So I have energy in by heat plus energy in by work plus all the mass and the energy in, which is enthalpy plus kinetic plus potential equals all energy out by heat plus all energy out by work plus the sum of all the mass energy out. Next step is to cross out the terms that doesn't belong. If my heat exchanger is not losing heat or gaining heat from the environment, my Q terms would all go away. So no Q in, no Q out. There's no work being done. And I assume the kinetic and potential energy change of the fluids entering and leaving are 0. So now it's just all mass energy in. So if I go back to my heat exchanger, I can find out that I have the refrigerant going in one place at point 1, right? Here is point 1 right here going in there, and I have also air going in at point 3. So I have here the mass flow rate of refrigerant times the enthalpy it carries in at point 1 plus the mass flow rate of air times the enthalpy it carries in at point 3 equals the mass flow rate of refrigerant out, and it exits at point 2, plus the mass flow rate of air out times the enthalpy it carries out at point 4. So there's the result of my first law. Energy in by mass equals energy out by mass. And there's 2 streams of mass energy in and 2 streams of mass energy out. So I'm going to go ahead and I'm going to take this and I am going to bring all of my air terms on one side. So on the left-hand side, I get mass flow rate of air times enthalpy at state 3, point 3 minus enthalpy at point 4 equals mass flow rate of refrigerant times the enthalpy at point 2 minus the enthalpy at point 1. And I can go ahead and take this a step further and replace the air enthalpy. Since I assumed constant specific heats, I can substitute that the change in enthalpy is equal to Cp delta T for the air. And since the refrigerant is not an ideal gas, I cannot make the same assumption. I'm going to have to go ahead and look up my properties. So with that, I'm going to have to go ahead and solve for the mass flow rate of refrigerant by bringing the refrigerant onto one side of the equation, and I get mass flow rate of air times Cp delta T of my air divided by the change in enthalpy of the refrigerant. Now, in this problem, I have all my knowns with the exception of the mass flow rate of air. Right? I can go back and I can actually solve for that pretty easily by using the ideal gas law, since air is an ideal gas. So pressure times volume flow rate is equal to mass flow rate times RT. Solve directly for the mass flow rate of air, and I get P V dot, or mass flow rate over RT. Right? That's the same thing as V dot over specific volume, since specific volume for an ideal gas using the ideal gas law is RT over pressure. So if I go ahead and solve for the mass flow rate of air, I can get an answer for that. And I'm not going to write in the numbers for this problem, but just kind of go through how to solve this. You guys can go ahead and solve it on your own. So the mass flow rate of air can go back and be plugged into this equation, and then the only unknown that you have left is the mass flow rate of refrigerant. So that is, again, it's a heat exchanger with the first law analysis where the boundary is around the whole heat exchanger. I'm going to go ahead and do a first law analysis now with the boundary around just the refrigerant. Right, so if we were going to go ahead and do an energy analysis or a first law analysis, energy in minus energy out equals the change in energy of the system. The change of energy of the system is 0 since it is steady flow, so I'm left with all energy in equals energy out. So that would be all energy in by heat plus all energy in by work plus all energy in by mass equals all energy out by heat plus all energy out by work plus all energy out by mass. So if I go back and analyze this, there's no work exchange, of course. And if I go back and look at the refrigerant itself, I can see that during this process, from point 1 to point 2, the temperature decreases. So the refrigerant is giving up heat to the environment. So there'll be no heat in, and there's no change in kinetic and potential energy. So I'm left with mass flow rate of the refrigerant times the enthalpy at point 1 in equals heat flow out plus mass flow rate of the refrigerant times enthalpy out. So if I bring my Q term to one side of the equation, I get mass flow rate of the refrigerant times H1 minus H2. So that's if I do a first law analysis with the boundary around the refrigerant. And then finally, for a first law with the boundary, so first law analysis around the air, same thing. First you write out your first law in its most compact form. Steady flow, so delta E system goes to 0. So I'm left with all energy in equals all energy out. So I get energy in by heat, work, and mass. Equals all energy out by heat, work, and mass. Now, crossout doesn't belong. There's no change in kinetic and potential energy of the fluid. There's no work interaction done. And this fluid is being heated up by the other fluid, so I have heat energy in plus the mass flow rate of air times its enthalpy that it carries in at point 3 equals mass flow rate of air times its enthalpy that it carries out at point 4. If I take this equation and I go ahead and solve for Q in, I would end up with mass flow rate of air times H3 minus H4, where I can simplify that further, where I take my delta H, and since it's constant specific heats for an ideal gas, I would go ahead and solve for, or substitute Cp delta T for delta H. Now, this is for an adiabatic heat exchanger. So in this case, the Q out from the refrigerant is equal to the Q in for the air. If this heat exchanger was not adiabatic and I had some sort of heat leak, right? I'd have to do a first law analysis where this first law analysis would change, right? This first law analysis, I would end up with some sort of heat term, right? Some sort of Q leak that gets incorporated into this where I actually have heat leaving the system, right? So this extra Q term would result in Q out not equaling Q in if there was a heat loss, because all of the heat given up by the fluid that's doing the heating to the other fluid, some of that heat would go into the other fluid, and then some of the heat would actually exit the heat exchanger. So remember, all this is based on the first law analysis. Try not to, I would not memorize all this. I would go ahead and try to make sure that you solve each first law analysis the same way, where you after you write down your assumptions in schematic, and if you need to do a first law analysis, you write down the first law's most compact form, cross out the terms that don't belong, expand it. For in this example, you would expand it E in equals E out into all the energy transfer terms, cross out what doesn't belong, and get it into a form that fits.